Hi, am I audible? Okay, I am Subrata Samanta and I am a teaching assistant for the thermal physics course taken by Professor Demal Banerjee this semester at NPTEL. So currently I am a first year PhD student at IIT Kanpur. Okay, so today we will spend a lot of time to understand the behavior of the real gas and then solve problems, some problem related to it. Okay, so I suggest you to do the calculations along with me so that you can check the answers and better understanding to the problems. Okay, so first share my screen and then let's start sharing. Yeah, my screen is visible now, right? Okay, so so far we considering the gas without any interactions. So we considering the gas without any interaction, without without any interactions. Okay, it's so called the ideal gas, right? So called ideal gas. So what are the basic underlying assumptions? So the underlying assumptions are underlying assumptions. So the basic underlying assumptions are that so again you think that the without any interactions, so that means the collisions of gas molecules are perfectly elastic. Collisions of gas molecules are perfectly elastic. And second, yeah, so collisions of gas molecules are perfectly elastic. This is the first assumption. That means that no interactions. Okay, so the collisions are elastic collision. And second, so this point is understood, right? So why they are perfectly elastic collision means that there are no interactions because there is no potential to extra force that on that. Okay, so it's a perfectly head-on collisions. Okay, type of things. So it's a perfectly elastic collision. There is no potential to force to that they collide. This kind of things. Okay. And the second assumption is that the volume of the molecules negligible. So the volume of the each molecules, that means the volumes of the each molecules negligible with respect to the container volume. Negligible with respect to the container volume. Okay, so that means a point like. Okay, so these are the basic assumptions for the ideal gas things. Okay, so how about for real gas? Okay, so how about for real gas? Okay, so the corresponding equations of state, the corresponding equation of state is given by PV is in RT. So under these assumptions, the corresponding equations of state PV equals to nRT. So where n is the number of moles, right? So n is the number of moles. Okay. So this is the ideal gas situations. So how about for real gas? However, Okay, so however for real gas, what things that happen, that the attractive force exists between the molecules when they collide, right? So attractive force exists exist between the molecules when they collide. So this giving rise to sticky collision. I will come to this point. What is sticky collision? Okay. So for ideal gas situations, we are considering the elastic collisions. Now for real gas situations, okay. So whenever the deviate from these assumptions, we are going to the real gas situations. So we are so deviate from these assumptions, we are going to the real gas situations. Okay. So first assumptions, let's say we break this, the collisions of gas molecules are perfectly elastic. Now we break this and we uh, allow a attractive force between the molecules. So this attractive force, what kind of attractive force? This attractive force is a weak. So when the molecules come close together, then this attractive force become applicable, and due to this attractive force they collide. Okay, so this collision is not a part elastic collisions because they are due to some potentials there, and due to these potentials they collide. Okay, so this collision is different from the previous collisions for the ideal gas situations like that. Okay, so ideal gas situations there is a no potential between the two molecules. Okay, so when they are just a random collision, head-on collisions. Okay, so elastic collisions. But in this case, they when they are close together, there are some kind of attractive force applicable on the molecules, and due to this force they collide. Okay, so this is called the sticky collisions. Okay, so this is clear or not? Okay, good. So yeah, so now suppose okay, so then at what kind of what temperature this thing happens? Suppose you increase the temperature, let's. Okay, so then what happens? So suppose you increase the temperatures. Okay, so that means particles kinetic energy also increases. Okay, just a minute. Okay, so minutes. So the attractive force exists between the molecules when they collide. That is called as sticky collisions. So suppose we increase the energy, increase the temperatures, and then the kinetic energy increases. Okay, so that then the colliding molecules to quickly separate again. So they collide and quickly separate again. So at high temperature, let's say we are considering two situations at what happens at high temperatures and low temperature. So at high temperature, colliding molecules to quickly separate again. Colliding molecules collides and quickly separate to quickly separate again. Okay, and at low temperature, the attractive force allow colliding molecules. So attractive force allow colliding molecule stick together. Colliding molecule stick together in a large enough and stick together and then uh, converted into the liquid phase and converted into the liquid phase. That means some kind of condensation happens at low temperatures. So that's why we are deviating from this ideal gas to the real gas. Okay, so when we are going to the low temperature things, okay, so that means the colliding molecules stick together due to this attractive force, and some kind of condensation happens and go to the another phase called the liquid phase. So we are first initially the condition of the gas molecules, and at low temperatures they are going to the liquid phase. Okay, so gas phase to liquid phase. So this kind of situations is not happens in the ideal gas. So when you are dealing with the real gas systems and putting the attractive force between the molecules, this kind of situations happens. Right. So due to this attractive force at low temperatures, and so these colliding molecules stick together and converted to the condensate and go to the liquid phase. And at high temperatures, the colliding molecule collide and quickly separate. That means it's some kind of again ideal gas like things. Okay, so why this point it becomes clear so when we go through the these details. Okay, so let's start with on examples. Okay. So okay, so we are considering this and this. Okay, so let's one example. So let's consider one example. So let's say there are n mole of gas in a volume V. Let's say there are n moles of gas in volume V. Okay, so okay, so now in mole of gas in a volume V. So attractive molecular interactions lower the potential energy by an amount. Okay, so let me go systematically one by one. So the number of nearest neighbor for each molecules. How to write? Okay, so number of nearest neighbor for each molecules. We are actually allowing the interactions between the two subsequent molecules, and we first know that for each molecules the number of nearest neighbor. How to write for the number of nearest neighbor for each molecules. So then Van der Waals first proposed a models. Okay, so propose a models to do this kind of approximations. Okay, so how to allow the interactions kind of things. Okay, so we consider that the number of nearest neighbor is proportional to the density. Okay, and we are considering that throughout the density is same. Okay, n by v. So the number of nearest neighbor at each molecules is proportional to the density. Okay, so then the number of nearest neighbor is proportional to the n by v. Right. So there is a n mole of gas, so it's n times n. Okay, so that's the total number of molecules and by v. And now we are, so the attractive intermolecular interactions. So now we are allowing the attractive intermolecular interactions. So attractive intermolecular interactions, they lower the potential energy, So initially ideal gas situation there is no potential energy, Now the potential energy comes into the picture due to this attractive potential. Okay, and these attractive intermolecular interactions lower the potential energy. Which amount? Because there is a n molecules, and the number of nearest neighbor each molecule is n by v, so is proportional to the n times n by v times some proportionality constant we call a. So this amount is n, the number of so n moles, that means n number of molecules, n times n a number of molecules, into this is the density, the number of nearest neighbors. So because they are actually calculating the potential energy, so and this is some proportionality constant, so some constant, because we have there is a proportionality sign, so is some constant is proportionality constant, and the number of nearest neighbor n by v, and n is the number of moles of molecules. Okay, so this is the total attractive total potential energy due to this collision, attractive potential. Okay, so then if we write this thing as a, so now let's say if we allow it that if we change the volume v, if we change v, right, if we change v, the change in energy, changes in this energy is actually minus n square by v square, just derivative, because if you change the volume, let's say v to v plus dv. Okay, so this due to this dv, these times of energy changes. Okay, n square by v square dv. So these energy changes can be thought of as due to this effective pressure. So energy means that force times displacement, and if we say that this is a force time, okay, so you can dimensionally write that this is force time area into dv, that means force time distance, right? This is area, this is volume, so it's force time distance. Okay, so the change, so you can write this is as the effective pressure P effective times dv. So when you go into the thermodynamics, you see that the work done is actually P dv. Okay, so this is a pressure, effective pressure times dv. Okay, so this energy change can be thought being as a due to effective pressure. So this energy change can be thought of as being to an effective pressure. To an effective pressure. So now our effective pressure P effective is minus n square a by v square. This is P effective. Okay. So up to this point is clear or not? Yeah. So okay, so then okay, so then things is now. So now we are going to. So here is some constant. We later will denote that what is the constants. So okay. Okay, so now physically what is actually happens. So suppose if there is a container, and we considering there is a molecules of there, gas molecules. So in ideal gas situations there is a no collisions, okay, and there is a no sticky collisions, all our collisions are perfect, okay, perfectly collision, there is a no attractive potential. So now we allowing the attractive potential, right, and due to this attractive potentials the fewer number of particles are actually fewer number of particles are what is it, yeah, fewer number of particles fewer separate particles actually at any instant of times it's okay, so at any instant of time fewer number of particles collides. So that means if you say that these molecules due to this attractive potential energy, so they collide with this the nearest neighbor of the molecules, and the fewer number of molecules actually collides with the wall, and then the pressure is actually in this system reduced. So physically we think that the ideal gas situation, what is happens that each molecules are quite random, and they actually at certain interval of time, so when we're calculating the pressure, that all the molecules are individually hit to the walls and gives the pressure. But in this case, this situation is not happens due to this attractive of this molecular attraction. Okay, so there are fewer number of particles are actually hitting to the walls and contribute to the pressure. Okay, so that means in this situation, the attractive case situations, the pressure is actually lower than the previous case. So the measured pressure, if you measure pressure, is actually lower than the ideal situations. So measure pressure or observe measure pressure for real gas actually lower than the ideal gas. Okay, so for lower than the ideal gas, if the measure pressure for real gas is lower than the ideal gas. So this actually due to this effective potential is a negative effective pressure. Okay, so but this again at the moderate temperature. So when we go into the high temperature of the real gas, that means again so as I previously said, at high temperatures the colliding molecule too quickly separate again. Okay, so then again we think this kind of, so when at high temperature limit, so these molecules is quietly separate too quickly separate again and hitting to the walls, so it close to the ideal gas situations. Okay, so when we are going to various kind of equations of state like van der Waals, Dieterici and Savos equations of states, all are the converted to the ideal gas in some limits. So that's limit is one of the limit is the high temperature limits. Okay, so physically if you think these are okay, so at high temperatures two molecules are colliding and too quickly separate again because their energy increases. Okay, so kinetic energy increases, so they colliding and too quickly separate again, so rather than the potential energy. So then this ideal gas kind of situations happens. Okay, all the molecules hitting to the wall, this kind of things. So if you measure the pressure of the real gas is lower than the ideal gas, so that means this measure pressure P is P ideal plus P effective, right? So due to this effective potential is actually reduce the pressure. So this is the ideal gas pressure, and due to this effective potential, effective pressure, due to this effective pressure, your measure pressure, that means experimentally with the measure pressure, that is reduced. So that means P ideal is actually P plus N square A by V square. Okay. So this N square A by V square actually compensated. Okay, compensated for sticky collisions. So we add this amount N square A by V square to the measure pressure is compensated for the sticky collisions. So we do not know that what is happening inside the systems. Theoretically, we build a model and how to know that there is a this kind of sticky collisions happens. Okay, so in that situation, so we only know this equation P V equals to nRT, right? But we write a equation when considering a molecular attractions. Okay, so then this is actually ideal gas equation. So if we replace P ideal by this amount, so what will we get? That P plus N square A by V square into V in R10. We get these types of equations. So this from ideal gas theke we get this because we are considering this so in this case again P is the major pressure. Okay, so it's the major pressure by the experimental law, and we are building a model that's we are adding to this major pressure this amount because we are allowing that the attractive potential reduce your pressure when we measure experimentally. Okay, so we add this pressure to compensate for this compensate for the amount to actually lose for the collisions. Okay, so now we are going to the second assumptions. What are the second assumptions? Second assumption is the volume of the each molecules negligible with respect to the container volume. So this is for the ideal gas situation. So the second assumption for the real gas, the second assumption is for real gas, the volume of the each molecule, there is a finite size, right? So finite size of the molecule, finite, let's say non-zero size of the molecules. Okay, so finite non-zero size of the molecules. So due to this non-zero size of the molecules, so that means that let's say container, and we are considering a molecule with a finite size. Okay, so radius, let's say r. Okay, and there is another molecule, all the molecules have a finite size r in the same size. Okay. So the in the van der Waals case, all the molecules have the same size, finite size r. So this molecule, it's not cover the whole volume V because due to this molecule. So this molecule is, so these types of molecule, so okay, so let's go to the different colors. Okay, so these molecules, so these blue color molecules is occupied a volume, let's say B, right? So this occupied a volume B. So this red color molecules, okay, cannot move through the all volume. Okay, so because they occupied some volume B. So the available space of the for this red color molecules is actually V minus B. Okay, yeah, so this is clear or not? Yeah, okay, so now there is in mole of gas, so effective volume is V minus NV because n mole of gas are there. So we are this is for the one case, and now the n mole of gas, so V minus NV, right? Because there is another molecules. So each molecules is a B. So the available space is too much reduced when we increase the number of molecules. Okay. So this is V minus NB. So now therefore the equations. So let's say this is A equation. So equation A becomes P plus M square A by V square V minus NB equals to A naught. Okay, so this is our van der Waals equation of states. The van der Waals. Okay, so this is the van der Waals equation of states. So considering the finite size of the molecules and the attractive interactions between the molecules. Okay, so now we are going to the okay, so now write the pressure in this form. Let's say P is in, okay, so for 1 mole N equals to 1. Okay, 1 mole of van der Waals gas. So there is a no definite real gas. So we build some models. The van der Waals did a models that van der Waals, and now we have Dieterici. They can another types of corrections. Okay, Sabasu. So there is no perfect model for the real gas. Okay. So in van der Waals case, for one mole gas, P RT by V minus B minus A by V square. Right. So this A by V square actually comes from the potential part. Potential energy means that the attractive potential energy. So now we are going to the high temperatures. So at high temperature, which term dominates? So at high temperature, P. So at high temperature, so RT by V minus P is dominant rather than the A by V square. Okay. So this term will be dominant. So at high temperatures, RT by V minus B will be dominant. Dominant continuous. So that means your pressure P is RT by V minus B approximately. So that means P into V minus B equals to. This looks like ideal gas. Okay, if you are not considering the V minus B, to say that your okay, so actually close to the ideal gas. Okay, so we are going to the ideal gas situations. So now at low temperatures, so let's plot the isothermal curves. So this actually best described through the isothermal curves. Okay, so in first considering the ideal gas, PV actually RT. So if we plot this P versus V, so at constant temperature, we plot the isothermal curve, means that the constant temperatures. Okay, so so at constant temperature, this curve is looks like this kind of things, right? So it's for ideal gas. Okay. So this is for the ideal gas. So let's denote this curve. Let's say this is T3, this is T2, this is T1. Okay. So your T3 is T1 is greater than T1. So this is your isothermal plot. Isotherm plot. Okay. So isotherm curve means that at constant temperatures, how pressure vary with the volumes. Okay. So now it's the same thing when we plot the this gas P actually T by V minus B by A by. Okay. So this is the van der Waals gas. This is the van der Waals gas. Okay, so then how the plots look like. So we plot these things. Okay. So first of all, we now choose the temperatures, right? So let's say we start at the high temperatures, right? So at high temperatures, as we said that previously, at high temperatures, is this P is actually looks like RT by V minus V. It's kind of ideal. Okay, so you have just a P times V minus B is nearly equals to RT. So that means it looks like a this kind of graphs. Okay. So at high temperatures, at high temperatures we get a this kind of curve. Okay. This kind of curve is high temperatures. Okay. So now we are lowering the temperatures. What happens when we lower the temperatures? So then we are not so at moderate temperature we are not using this kind of approximations. Okay, so this kind of approximations is not happens at moderate temperatures. So let's write down this in so how to write in this form, that P VQ minus PB plus RT V square plus AV square, sorry, AV minus AB equals to 0, right? So at any temperatures, right? So this is a cubic equations, as you see that V square VQ V square V cubic equations. So that means when we lowering the temperatures, so we are not using any kind of approximations here. So that means there is a must be there is a three roots. Okay, so at any temperature, let's say, so at high temperatures, so this is, let's say, temperature scale. Okay, temperature is increases, so at high temperatures it looks like a ideal gas. Now we lowering the temperatures. Okay, let's say at very small temperatures. Okay, so at very small temperatures, so there must be a three roots of V, right? So that means the curve is actually looks like this kind of things. So at any particular pressure, okay, at any particular pressure, how many roots there? One, sorry, yeah. So 1, 2, 3. Right. This kind of situations happens at some below some lower temperatures. So now what is the problem in this case? So that means if you go through this high temperature to low temperatures slowly, okay, so at that one point if you found that so this kind of situations happens, and then okay, so at one point we found that the point of inflection. So in this case again three roots. So this one, this curve. Okay, so let's mark this red curve. Okay, so what is the problem for this case? Okay, so this is a green curve. What is the problem? So in this case, if you say that del P, okay, so this slope, let me draw this slope. What is this slope? This slope, that means the del P, del V at constant temperature. So this is at particular temperature. Let's say T1, this is T3, and this is T2. So at T1, at particular temperature T1, each positive or negative. In this case, the del P slope. Yes. So this is positive, right? So that means what does this imply? So this implies that if you increase the volume or if you increase the pressure, that means the increase the volume as well. Okay. So similarly, we conclude that the del V del P is also greater than 0. So that means if we increase the pressure, the volume is increases, right? But this is not the case, right? So increase the pressure, that means the decrease the volume, we know, right? So that is the physically stable system. So when we increase the pressure, that means that decrease the volume, or if we increase the volume, that means decrease the pressure. But in this case, we are getting that the opposite situations. Okay. So that means that system is unstable in this case. Okay. So this is an unstable system. So this is an unstable system. So that means when we lowering the temperatures, okay, after certain temperature, let's say this is T2, okay. So after certain temperature T2, this kind of unstable go to the unstable system. So and this kind of critical behaviors, okay. So that this phenomena happens when the temperatures. So when let's say write down the explicit, when the temperature is lower than a certain critical temperature, lower than certain critical temperature, in the figure we saw that this red curve, okay. So it's the T2 temperatures. So certain critical temperatures, when the temperature is lower than the certain critical temperatures, a system goes into the unstable state, okay. The system goes to the unstable state. So that curve is called the critical isotherm curve, okay. So and this curve there is a no minima, there is a no maxima, okay. So in this case we say that there is a one minima, okay, and there is a one maxima, right. So there is a one minima, one maxima, but in this curve, so the critical isotherm curve, there is a no minima, no maxima, it's a point of inflection. So when the temperature lower than the certain critical temperature, system goes to the unstable state, and the corresponding isotherm curve is called the critical isotherm. Critical. Okay, so it's called the critical isotherm. So this point is clear that why this system is goes to unstable when this del P is greater than 0. Yeah, so that means when you try to compress the gas, it gets bigger. Okay, so when you try to compress the gas, it gets bigger size. So this is actually unstable situation. Okay. So this isotherm curve, okay, does not have a maximum or minimum, but shows a point of inflection. So this does not have a maximum or minimum, but shows a point of inflection. So this point is called this point is known as critical point. Critical points. Okay. So this point. Okay. So this point is the critical point. So only one point with respect to these points, okay, all P, V and T are just called is the PC, VC and TC, the critical point. So PV and temperature, so P is called PC, P is called VC, T is called TC at this point. So at this point P is called PC, V is called VC, okay, and this T2 is actually TC. So this is actually TC, the TC isotherms, and one particular point where this happens, there is no minima, no maxima. So with respect to this point, it's called that the critical points. Okay. So okay, so what it means that, so when we go into this, when we dotted, let's say curve, this kind of situations. So that means this is the gas phase. Okay, this is some other phase called the liquid phase. Okay. And your critical point is to stop this between the two phases. Okay. So when you go into the gas phase to lowering the temperatures, we liquefy the gas, we go to the another phase. So this is called the triple point. Triple point, this means that the critical points. Okay. So okay, and so now we calculate, let's say for van der Waals gas, how to calculate PC, BC, TC. So it's easy. So once we know the conditions, how to get this critical points. So for P, actually, let's say RT by V minus B and A by V square. Okay, and we so what is the conditions for this case when we calculate the PC, BC and TC? The condition is that the point of inflection, and there is a no minimum, no maximum. So that means the del P, the first derivative with respect to temperature is 0. So where 0? At critical point, PC, VC, TC. So at this point only this is 0. Not this point, but this 0 and this also 0. Delta P, delta V2 at D, PC, PC, TC. Okay, so there is a minima, right? So this point is a minima, and this point there is a maxima. In this point of PC, VC, TC 0. Sorry, del P 0, but not del 2P, del 2P 0. They positive or negative depending on the maximum or minimum, right? But in this triple point, both first derivative are 0 as well as the second derivative of 0, because their point of inflection, there is a no minimum, no maximum. So that means when you doing these calculations or writing this is 0 and this is 0, so mention the point at which point this is 0, right? So this PC, VC, TC at this point this is 0, and similarly for del 2P, del 2V, T at PC, VC, TC both are 0. Both are simultaneously 0. That means that we are pointing to the critical points. So if we say 1 0 and another is not 0, that means we are going to the another points, not the critical points. So at critical points both are 0, right? So then we can just calculate, we get so once we calculate del P del V at this point, we get this kind of things minus RTC by TC by V the whole square plus 2A by VC the cube equals to 0. So in writing these equations, all are calculating at this point PC, VC, TC. So we replace this PC to TC, and then we can claim that this is 0, right? Similarly for del 2P delta V2, so 2 RTC VC by V the whole cube minus 6A by VC the whole to the power 4 is 0, right? So this actually is a del P del V T equals to 0 gives, and this is del 2P delta V2 T equals to 0 gives. So when we writing this is equals to both are 0, we make sure that we are writing in terms of PC, VC, TC, at which point we are calculating, and we claim that this is 0. So now, then we can after some little algebra, so we have get this just equating these two. Okay, so we are getting this RTCH 2A by VC minus B the whole square by VC cube, right? So it's equating 2, and we get this so once you know from, okay, so no from this equation RTC Yeah, yes, so we get this, right? So from this equation and another equations we also get sorry, so these equations, yes, from these equations, and these equations we get RTC is 3a p minus b the whole cube by bc the whole to the power 4. So yeah, so now we are equating these two right hand sides because they are RTC. So equating these two, we get um, sorry, this is BC. So BC minus B into 3 by BC actually 2. So this implies that BC is 3B. Okay. So this BC is 3B. Now we put here BC and we get a DC. Right. So put one of these equations. So we get DC, just put a 3a 2b the whole cube or 3b the whole to the power 4. Okay, so now we see that 8a by 27 RB. Right. So this is your DC. Now how to get PC? I just put into the equations of state. So okay, the equations of state is valid throughout the whole regions, right? So at any point if you are considering in this PVT plane, so equations of state must be valid, okay? Because we are plotting the equations of states. So that means that PC actually RTC by PC minus B by A by PC square, right? So RTC PC minus B, yeah. So once you put this TC value and BC value, so we get RTC is 8A by 27 RB times BC minus B 3B minus B minus A by 9B square. Okay. So yeah, so there is a no R. 27B, yeah, R cancel. So that means we are getting this 4A over 27 B square minus A over 9B square. So we get A over, just check that, 3, yeah, A over 27 B square. So this is your piece. Okay, so this is a critical pressure. Critical pressure. Okay, and this is your critical temperature. Critical temperature and critical volume. So similarly, suppose you have given the another equations of states. So what about the equations of state? We first calculate this, and we know that at PC, VC, TC points, the point of inflections have here. So let's say we have given some another equations of state. Okay, so then similar kind of things happen there also. Okay. So when we lowering the temperatures at some, after some temperatures we are getting unstable situations. Okay. So that means we are actually going to the another kind of things, phases, or so similar kind of situations happens at every equation of states. So we are calculating this del P and del 2P delta P to equals to 0, uh, end of this we are getting this BC. So once we know this ATBC, we calculate that the critical coefficient. So critical coefficient, so this is defined as eta c. Okay, so it's RTC by PCVC. Okay, so this eta c RTC by PCVC, we just put in this form. Okay, so TC is 80 by 27 RB and by PC is A by 27 RB, so it's cancelled. So RTC is 8A by 27 RB by 27. So PC is A by 27 B square into PC is 3. So that means you are getting 8 by 3. These are cancelled. So 8 by 3. So now we measure this value with the any kind of gas, let's say H2N2 or something which gas actually close to this model. Okay, and the deviate from this value with the other gas are clear signature for that we are making these assumptions for the van der Waals gas are not actually correct, so you have to modify again. Okay, and that leads to the different of gas like Dieterici gas, Waals gas. So they are modified in some other way. Okay, so I'm not going into the Dieterici and Waals gas. Okay, how they modified further and get leads to the another equations of masses. So another equations of states. So, but you know that how to calculate this critical coefficients and RTPC, this is the critical point. So it is very straightforward. Once you know that what is happening, why we need to calculate this specificity. So you just put into the formula and you can straightforward calculations. You calculate, we get the values. So okay. So one more point is that what is the ACBC? A and B are constant. So B is the account for the A constant is the parameterage is the strength of the intermolecular interaction. Parameterage is the strength of the intermolecular interaction, and similarly the B constant which accounts for the excluded volumes. Accounts for the excluded volume. Okay, so therefore the dimension of B must be the dimension of volume. Okay, what is the dimensions of place A? So just we know that the two dimensions, when we add the two quantities, so dimension must be same. So that means the dimension of A is so the dimension of P times dimension of B square. Right. Okay. So now so one simple way to get the ideal gas equation, just put the A and B 0. So let's say P actually RT by P minus B minus A by P square for 1 mole of gas. So we put A equals to 0. That means there is a no strength, that means no interaction. Put B equals to 0. No ideal gas equation, no excluded volumes. These molecules have point-like structures. Point-like, okay. So there is a no finite size things. We are going to the ideal gas. Activate. So this is the limit that A goes to 0, B goes to 0, I go to the ideal gas. So whatever you modified the gas, okay, modified the equations of states, okay. So in the limits that A0, B0, we are going to the ideal gas. Okay. So once you turn off the interaction and the finite size effect, so go to the ideal gas. Okay. Okay, then suppose I want to ask that what is the energy of the van der Waals gas? So what is the energy of the ideal gas? It's the energy for ideal gas. So ideal gas only kinetic energy. So how to know that the kinetic energy at particular temperature is T? For ideal gas. Hello. Okay. So at particular temperatures, how to know that the how to know the kinetic energy from equivalence of theorem? Yeah, but three is actually one molecule, right? One atom. But we are considering there are some n moles of gas, or so this is actually F by 2 kVt. So F is the total number of degree of freedom. Right. So for one molecule is the 3, and n molecules, so 3n. So F is 3n. So in general, there is a, if there is a degree of freedom, so F by 2 kVt, right? So the kinetic energy is the total energy because there is no potential energy. So now for van der Waals gas, the potential energy comes into the picture, right? So F by 2 kVt is still there, right? So kinetic energy part F by 2 kVt is still there. So now the potential energy. So what is the potential energy? So as I said the beginning, that attractive intermolecular, so this line, attractive intermolecular interactions lower the potential energy is this, right? So that means if we considering the energies for 1 mole, it gives a by V, right? So when you put the n equals to 1, it gives a by V, right? And this is a lower the potential energy, that means a negative sign. So this is sign must be important. So this actually minus a by V for 1 mole. Or more specifically, if we write let's say 3 RT. Okay. So R is NaKB, right? And we are considering 1 mole, so Na1. So more specifically this for 1 mole of van der Waals gas. So this is exactly derived. So when you study the statistical mechanics and write down the percent function and exactly derive the internal energy, so you get exactly the same expressions. So there's a different thing when we study the statistical mechanics. We will do that, how to calculate the internal energy from the equations of states. So first build the percent function and then derivative with respect to the percent function, some variables. So we get a energy, and this energy is exactly the same thing. But here intuitively we say that what is the energy. Okay. So with proper sign convention, that the potential energy is lower the potential energy. That means initially the potential energy is zero. Now we lower this potential energy due to this attractive potential. So attractive potential means always the negative potential energy. Okay. So that's why they are attract. So inevitably we can write this the energy of the van der Waals is this 3 by 2 RT minus A by P. So in this case, once you think that for the ideal gas situation, the energy only depends on the temperatures, right? So now the energy is dependent on both temperature and volume, right? So this is a crucial point, that energy now is depends on the temperature and volume, but in this case, its energy only depends on the temperatures. It only functions on the temperature, but now the energy is depend on the temperature and volumes. So similarly, if we go into the Barthelot equations, we see that the Barthelot equations is actually so the pressure is the modified pressure is not the only volume dependence, is also the temperature dependence. So what is that the equation of state? Let me check. Yeah, there's some kind of P minus V square, right? So P plus N square A by T V square and V minus NV equals to N. This is right, or I think this is right. Yeah, I think this is right, right? Okay. So in this case, we say that this pressure is not only the volume dependence but also the temperature dependence. So it also the temperature dependence. Okay. So till now, any questions? So next we are solving some assignment problems, and let me check what is the problems. Okay. So this is the So this is the particular equations of states. Barthelot equations of state. Hello. So is there any questions? Hello. Okay. So let me share my screen. Yeah. So this is the Barcelona unification substates. Okay, so P plus N square divided by V square. So in this case, you see that the pressure effective P effective is depends on both volume and temperatures. Right? Depends on volume and temperatures. So this is not the case that always the temperature depend volume dependence, but so when you go to the different model and different equations of states, we see that so in general that that depends on both temperature and volumes. Okay, so now we go to the some solve some problems and in the week 6 assignments. So I think once you know the formula how to calculate okay, so first of all, you know that this BC actually 3B, BC, so also write the things one more and then, so BC is 3B, BC is A by 27, A by 27, yeah, A by 27 B square and AD by 27 RB. So A by 27 B square and PC is 80 by 27 RB. So we write down that B in terms of BC by 3. Okay, and once you know the B, we write down the A in terms of PC and BC, right? So yeah, so A is actually, let's say, right, the PC times 27 PC square over 9. So 3 PC square. Okay, so given the PC and BC, we can calculate so given the PC and BC, so we calculate this kind of things. Okay, so in the assignment, what is the ask that? Yeah, so calculate yeah. So in the assignment, let's say given PC. So given PC, okay, some 2.3 into 10 to the power 6 Pascal, and TC is, let's say, 100 Kelvin, right? So we calculate A and B, the van der Waals constant, calculate A and B. Okay. But we know that B actually VC by 3. So then we can replace this VC, which goes to, because the data is given is PC and TC, right? So we can replace VC is to, how to replace that? Once you know that the PC, so this is the eta C is at PC by PC VC. This is no, you get the added thing, right? So once you note that the VC is thinner at TC by PC, right? So then we put that VC is 3 by 8 at TC by PC. So then the B is actually at TC by 8 VC, right? So now put that TC and BC, we get a B, right? So quickly calculate this thing. Similarly, so A we know that the 3 PC and VC square. So we put that VC in terms of RTC PC. So it's 3 PC and VC square is yeah, so 9 over 64 R square PC square by 8.12. Yeah, good. Yes. So then okay, so then R square PC square is by PC square, so that means 27 by 64, 27 by 64 R square PC square by PC. What is that one? So the RL value is given, right? 8.3 on 4. Meter to the power of 6. Let's cross check. Meter to the power of 6 or 4. Yeah. So this unit is that the meter cube per mole, and this is 4. What is it? 4? Yeah, 0.410. The unit is that Newton meter to the power 4 by mole square. Right? Yeah. So look at the orders. Okay. So the B, the volume corrections, its order is 10 to the power minus 5. Right? Am I audible? Hello? Yeah, okay, just a minute. Yeah, so now focus on the orders. Okay, so what is the B? So B order is the order of B is 10 to the power minus 5, and the order of A is 10 to the power minus 1. Okay, so that means the strength of the interactions is so this order is important. Okay, so the A order, what is the order of A and what is the order of B? Okay. So volume correction is too small, means that the B minus B. Okay, so the volume is too small, but the strength of the interactions is order of 10 to the minus 1. Okay. So for different model means that different equations of states we are calculating the same thing, but the order is almost same. Okay, so it's 10 to the minus 1, or A is order is 10 to the minus 1, and B is order 10 to the minus 5. So this order is maintained. Okay. So it's not that the A is we get the, if you build some model for the describing a real gas, and you get the A is the order of 10 to the minus 5. Okay, so this kind of situation is experimentally excluded. Okay, so please cross check when you calculate these things. Okay, so similarly A and B given, and you calculate, let's say, the P, right? So the same way we can know. So suppose A and B are given, we calculate P. So using this formula, and so given the A and B, we calculate PC, DC. Okay. So this kind of things happen. So okay, so now okay, so now closely going to the okay, so just for the outlook. So we so what is the dietetic equation? So DIE so dietetic equations. Okay, so in this case, the P, the pressure is RT by P minus B into exponentially minus E by RT. So that means the pressure correction is not that P plus A by V square, but it's a series. Okay, so when we expand this exponential minus A by RTB, so it's 1 minus A by RTB plus 1 over 2 factorial A square by R square T square V square plus dot. So the pressure correction is actually included series and we get a exponential. So they first the dietetic modified in this way. Okay, so and the equations of state corresponding to this. So the volume correction is still the same. So that we are considering that each molecules have a finite size of B. Not that this molecule finite size B, another molecule is again the different 2B, 3B, this kind of thing. So all molecules have the same size. Okay, but the pressure correction is the modified in a different way. Okay, so we're calculating the series of things. So at again the some low density limit we have go to the van der Waals gas and again further limit high temperature limits go to the ideal gas. So these limiting cases are always observed. So when we go from one model to another model and then you can build another model. So first cross check that if I get a proper limits, we go to the previous model or not, right? So this kind of things are always you cross check that that some limits we are get back to our previous equation, and then we can claim that yeah, so this kind of modifications can be happen. So yeah, so now for this case if you calculate let's say del P del V at T at particular PC equals to 0 this point, and similarly del to P del to V at constant temperature PC is 0, we can calculate that. So once you calculate this thing, okay, so you get this kind of result is TC is A by 4 RB, PC is A by 4 E square. So E is the log E, okay, so this E, so this E, yeah, the logarithm E, and then it's B square, okay, and VC is 2. Okay, so once you calculate this eta C, the critical coefficient, eta C, this is actually RTC by PCVC, we get that the E square by 2. Okay, so previous case we found that this is a thing. Okay, so yeah, so previous case we found that 8 by 3, right? This critical coefficient we found that the 8 by 3, but in this case we found that E square by 2, right? So that means the critical coefficient is different. So that means let's say we are tabulated some gas, let's say any gas, argon gas and Kr gas and xenon gas, right? So these are the real gas, okay, and we are write down the values of PC by RTC. It's equal to 1 over eta C. This is opposites, okay, so 1 over eta C is PC by RT, we have written this value is 0.287, 0.292, 0.291, 0.290, right? So that means if we say that for this case of gas, so once you written for 1 over eta c, you just calculate, and so this result is actually 0.271. But in the previous case, for Van der Waals gas, if you calculate this 1 over eta c, it's 0.375, right? So that means for this for this kind of gas, okay, so it's a noble gas, okay, neon, argon, xenon, okay, this kind of gas, the eta c tells that the values of eta c 1 over eta c, okay, tells that the Van der Waals equations of state is not the whole story, okay. So the Van der Waals equations of states not the whole story, because we get a 0.375, but we are getting too much lower value, okay, 0.287, 0.291, this kind of things. So in this case, the dietetic equations of state somewhat correct model for describing this kind of gas, because we get a 0.27. Okay. It's closely related to these values, okay, of these gases. So that means for these gases, dietetic equations of states is a good model to describe this kind of gases behavior in this equations of state theoretically, okay. So in this way, we again that some other gases we see that again they are deviate from the this value, okay. So that means again we have to further modify, okay. So then the finally the Saab also which modified further this equations of states, okay. So they modified in both this pressure, both the pressure as well as the volume, okay. So they not consider that each molecule have a volume is b, right? So each molecule is volume is a b, another molecule is b minus 2b, this kind of things, okay. So in this way they further modified, okay, and end up with the equations and calculate this eta c, and they close to some other kind of gases, okay. So in that way, so we can write a virial expansions for more in general gases, okay. So we can write the virial expansions, okay. So HPV by RT is 1 plus P by V plus C by V square plus a series of these expansions, okay. So and this coefficient is called the virial coefficients, okay. So this is in general, okay. And we are calculating for separate gases what is the coefficients, okay, B and C, okay. So these are called the virial coefficients. So this B and C are called the virial coefficients, okay. So this is a general virial expansion series, general to the modified the ideal gas equations in a, so once you know that the PV RT by equals to 1, okay, so this is your ideal gas equation, and it modified in terms of 1 over V, 1 over V, 1 over V square we add, okay, and so on. So this way we modified the ideal gas equations to a real gas equations, okay, and this expression is called the virial expressions, okay. So so then V and C is called the virial coefficients. So now we calculate, let's say for Van der Waals gas. So Van der Waals gas, you know that the PV is RT by V minus V. Sorry, I think this is P is RT by V minus V. Yeah, so it's minus A by V square for 1 mole gas. So we can write this RT by 1 by V minus V all to the power minus 1, okay, and minus A by V square, okay. So then then there's the PV by RT, written this 1 plus P by P plus P square by V square minus A by V square plus P cube by V cube plus dot. So that means that this 1 plus P by V plus, no, 1 minute, I think that is okay. Oh, sorry. So this is a V actually. Okay, because we are A by V square, we are multiplying with this thing. So this is a V. Minus, so there is RT. Yeah. So there is A by RT. Yeah. So that means it's P minus A by RT 1 over V P cube by V cube plus. Okay. So that means the second virial coefficient is Bt. Is this, so this is a second virial coefficient, right? So this Bt is actually B minus A by RT for van der Waals gas. Okay. So just put in the expenses and compare with this 2, and this is a virial expenses 1. Okay. So comparing equations 1 and 2, we get that Bt actually this. So this actually comes from the comparing equation 1 and 2. So now we calculate the the boil temperature defined at where the second virial coefficient is vanishes. Okay. So the boil temperature where there is Tb, it implies that P at Tb is actually 0. The second virial coefficient is vanishes at temperature. Okay, so this temperature is called the boil temperatures. So that means that B minus A by R Tb is actually 0. So it implies that Tb is A by Br. Yeah. A by B, right? So once you know the A and B value, once you know the values of A and B, we calculate the boil temperatures for van der Waals gas. For different gas, this leads to be different results. Right? So if we write down the, let's say put an A and B in terms of PC, VC, TC, and so what is the values of for van der Waals gas A in terms of yeah, so A is actually TC, PC. Yeah, so A is 27 by 64 R square T square by PC. So then dB is 27 by 64 R square TC square by PC, and R times B is what is the value? for B. So we check that the B is actually 8TC, sorry, RTC by 8BC. So now we just calculating, we get 27 TC by 8. So this is the boil temperature related to the critical temperature. So TB is the boil temperature is 27 by 8 steps. So then you can solve the problem using this formula. So once you given this A and B or TC, okay, so anything is given TC or A and B, so you can calculate the TB boil temperature for van der Waals. Similar way we can expand the equations of state in this way. Okay, we can expand the equations of state in this way. We get the boil temperature for, let's say, lactic gas, Berthelot gas, okay, or Sahabasu gas. Okay, so we can calculate these things. So now, so the critical constant you calculate for the different gas. Okay, so once you know that the specificities, you can calculate this critical constants. And okay, so now we are going to some problems. So let's say if platinum resistance thermometer. Okay, so by the way, so at this till now, have any problems? At any point, if you're not understanding, explain again or okay. Okay, so now we're doing this formula is slightly different things. Okay, so a platinum resistance thermometer, let's say reads some 1.35 ohm at 0 degree centigrade, and let's say okay, tabulated, or we can write this thing. So 0 degree centigrade, and let's say 50 degrees centigrade, which is 1.35, and that's a 2.17. So and a 2.89. So we are considering at the bath temperatures. So at bath temperature is 2 point, let's say, sorry, 2 point is not that, okay, so it's 1.97, okay, at bath temperatures. So this is 100 degrees centigrade, right? So if the true temperature of the bath is let's say, what is the bath temperature? So the bath temperature, let's say 56 degrees centigrade. Okay, so calculate the values of the calendar correction factor. Then the calculate the value of the calendar correction factor. Okay, so how to calculate calendar correction factor? So okay, so your bath temperature is 56, right? So first of all, you calculate the theta p. Okay, so I think that defined in the class that once you know that the theta p is the formula is that the 100 times r theta minus R0 by R100 minus R0, right? So R means the resistance at this temperature, right? So if you know at R0, so at 0 degree centigrade, what is the resistance is 1.35, and R100, you know that the 2.17, right? And yeah, so then how to calculate the theta? Yeah, so okay, so then just put this thing. Okay, so we get yeah, so any comments? Just put in the formula, right? So if you know that the 100 times what is the earth theta, so you do not know the bath temperature, right? So initially we do not know the bath temperature, we have calculated the correction factors. So this is a true temperatures, right? So we are actually calculating the bath temperature and deviate from this true temperature is actually the correction. So 100 times earth theta, this is the resistance of this bath temperature is 1.97, minus R0 is 1.35 at 0 degree centigrade. Now our hundreds is 2.17 minus 1.35. Okay. Just quickly calculate and tell me the answers. Yeah, 73.1 degrees centigrade, right? So then actually corrects and so now the calendar corrections factor. So calendar corrections factor is that it's delta. This is your calculated estimated and your true temperature, let's say 56 degrees centigrade, right? So the calendar corrections factor is delta, actually the mod values of theta minus theta p by theta by 100 the whole square minus theta by hundreds. Okay, so this is a theta p, and you know that the theta is the true temperatures. Okay, the true temperature of the bath is 56 degrees centigrade. Okay, so that means a 56 minus 73.1, so 56.0 minus 73.1, and the mod and divided by, so theta, if you know that the theta is 56, so 56 by 100 the square minus 56. So we calculate and you get some results. So, and this is your correct results. Yeah, so calculate. 69. If you divide it by this, too large. Let me check. 69, how to get this thing? Oh, 1 minute. 56 by 100 and 56. 33. Yeah, 1 minute. Let me check. Yeah. So now we are considering that the 56. Yeah. So we are considering 73 theta p and considering the two temperature is 56. Yeah. So the process is the same. Okay. So let me check. 66. Yeah. Okay. Okay, so whatever you get, you can, but in the same way, we can calculate for different set of data. We can calculate. So you get the same answer. Right? You get the different answer, and I hope you get the answers that written in the question. So yeah, I use actually the wrong. I choose the some kind of different values of data. Okay, so that's why I get this bad answer. So we choose the data properly, and so you get a correct answer. I mean, so the reliable results you get. Okay, so next one thing we have to discuss. Okay, so suppose a system A and another system is B. Okay, and there is another system is C. Okay, so let's say A is thermal equilibrium with C. So thermal equilibrium means that when you connect with a bath, let's say, okay, so means that so let's say T1 and T2, the different temperature T3. Okay. So the A system has temperature T1, B system has temperature T2, and C system is temperature T3. We connect with these two systems. So after some time per, they are going to the steady state and their common temperature T. That means they are thermal equilibrium, right? So their common temperatures, they reach the common temperature at T. So when you connect the systems, after sometimes they reach the steady state and the temperature of the system or the whole systems, now the weak systems, so whole system in thermal equilibrium, that means they share the common temperatures T. Okay, so this T is common temperature. Okay. So this is the thermal equilibrium means that. Okay, so now we say that the A and B are in thermal equilibrium. That means after certain temperature, both the temperatures same. Now T is the system C is the defined temperature T3. right? And B and C again we connected, and after sometimes they are thermal equilibrium, right? So that means A and C are thermal equilibrium or not. So we have connected them again. Share the common temperatures. So that means A and C are thermal equilibrium or not. Let's look at the temperature. So A and B are two systems connected with a, and after sometimes they share common temperature T. That means they are thermal equilibrium, right? So similarly, connect B and C, and after sometimes they share common temperatures, right? So then A and C are in thermal equilibrium or not? So all are the same temperature, right? So once the okay, so first of all, A and B share the common temperatures. So B has a temperature T, A has a temperature T. Now you connect B and C. So that means B and C share the same temperatures. And you know that the A and B share the same temperatures. Right? So that means A and C obviously share the same temperature. Sorry. If the system is hold the system is steady states. Okay. Because B and C are the same temperature. A and B are the same temperature. Sorry. So you can ask in the opposite way. Suppose A is not thermal equilibrium with B. B is not thermal equilibrium with C. Right. So that means that does not mean that A and C are not in thermal equilibrium. So they may be thermal equilibrium, right? So A and B, they are not thermal equilibrium. B and C, they are not thermal equilibrium, right? So that means the middle persons actually problematics. But A and C may be in thermal equilibrium, maybe, may or may not be. But the B part is problematic because B part is neither thermal equilibrium with A or C, right? But A and C, it may or may not be, maybe or may not be thermal equilibrium. But the conclusion is maybe thermal equilibrium. Okay. So this thermal equilibrium part is clear or not? Still doubts. So in this case, that the B is problematic. B is neither with thermal equilibrium with A or B, C. But A and C may be thermal equilibrium because. So in this case, so this is the opposite case. That the two things are opposite case. So here that the B is the again the actual thermal equilibrium both A and C. So that sees that the A and C are thermal equilibrium because B is the middle guy that is responsible for the thermal equilibrium to A and C. Right? But in this case, the B is again responsible for the maybe it's related to the thermal equilibrium with A and C. Because they cannot share the same temperature T1, cannot share. They share cannot temperature same temperature T2. So that means A and C share the same temperature. Maybe. Maybe. Okay, so yeah, I think all of the assignment problems are most of the assignment problems are discussed. Okay, so and you just changing the data or the related concept to discuss here and we just apply we get to solve the problems. okay, in the assignments, as well as you pick out any problem from any books and try to solve it, any problems. So then write your questions in the next live sessions. So I'll be happy to answer these questions. Okay, and so the concept is first. Once the concept is clear, so whatever you have to deal with the problem. So your first steps is must be clear. So okay, at first steps, what do we do? Okay, what should we do? So once this is clear, then we can straightforwardly go through that and solve this problem. So first your concept must be clear. So your concept is clear, then we can know that where actually we start these problems. Okay, start to solve these problems. So this kind of things, and so yeah, so more practice, do more practice on the problems. There are too many books. Okay, they are in the literature, so you just go through this and pick up any problems, okay, and try to solve this. So if any face any problem, so rise and in the next live session. So yeah, so I think there are yeah, so the from the next week, so we start the thermodynamics part. Okay, so we start from here. Okay, so this is actually the zeroth law of thermodynamics. So this is actually the start of the zeroth law of thermodynamics. Zeroth law. Okay, so this is actually the zeroth law of thermodynamics. So this tells that the which system, when the system is thermal equilibrium or not. So we go in the next live sessions. We are discussing that what is the first law, second law, third law, this kind of things. Okay. Slowly go into the third law. Okay. So first we discuss the first law, second, and then slowly go into the third law of thermodynamics. Okay. And this is the very naively we say that the zeroth law of thermodynamics. So it's the equilibrium types of things. Okay. So okay, then yeah, so yeah, okay, then let me stop here and we will see in the next sessions. Okay, are any questions or hello? Okay, though, so we'll see in the next series. Thank you.